So I think we should start. So today we have Axel Kleinschmidt from the Albert Institute in Potsdam. So Axel has been contributing to the uncovering of the infinite dimensional symmetries I have mentioned for a long time. He made very important and decisive contributions to the field. And today he will discuss the question on how to include fermions, spinors, in the Kac-Moody symmetry, which has been revealed, or perhaps by the billiard. So I will let Axel speak, and as I said, if you have questions, please don't hesitate to interrupt, and I will repeat the question so that Axel can hear it. Okay, so please go ahead.
Thank you very much, Mark, and thank you for the invitation to give this talk here. And yes, so I will discuss some work that has been going on really over quite some time now. Most of the results I will discuss are in collaboration with Thibaut Damour and Hermann Nicolai, but of course there are many other people who contributed to this who I will highlight along the way. And the topic of the talk is really about the symmetries of maximally supersymmetric theories, supergravity theories. And let me just start by a very gentle introduction to review some of the very deep and long-known results about hidden symmetries of toroidal compactifications of maximal supergravity. So this goes back to work by Eugène Crémer and Bernard Juliat. When you start with 11-dimensional supergravity, and there is a unique one in 11 dimensions, and do a toroidal compactification or toroidal reduction on an n-dimensional torus, it was found back then that scalar fields that are present after reduction describe a certain scalar coset manifold. So these are very special scalar terms that you obtain in this case. And let me show you in more detail what kind of scalar coset symmetries you obtain. So if you do a one torus reduction, the coset is rather boring because it's just one-dimensional. It's just, well, maybe I should have written plus or minus one here. It's just the dilaton that you get from the reduction. There's only a single scalar, but as you keep reducing, the scalar coset becomes more and more interesting. So on the right-hand side, you can see the Duncan diagram that is building up in this reduction process. And starting from the compactification on T6, actually the symmetry groups you get are exceptional in the Cartan classification. So you get E6, E7, E8, which is the symmetry when you reduce from 11 dimensions all the way down to 3 dimensions. And then it was also found that when you continue this reduction to 2 dimensions, so on the 9 torus, you get E9 symmetry. And it was conjectured by Bernard Juliat already in 1982 that when you go one step further, you would get E10 symmetry in 1 dimension. And there's also a lot of work that I'm not going to touch upon so much, which is related to 11 symmetry, mainly promoted by Peter West in a slightly different context than I have in mind here. That's why I'm not going to talk so much about that. So these are the hidden symmetries that you obtain from the dimensional reduction. So this is a very, as you could see from the way the Duncan diagram was built up, it's a very nice and consistent and systematic story. And I believe that you have seen part of this in the lectures, if I understood correctly right now. So there was, after these old ideas about E10 and one-dimensional reductions, there was new momentum in this development, which started with the analysis of this Belinsky-Khalatnikov-Lifshitz cosmological limit when you go close to a space-like singularity and you look at the supergravity equations of motion where they simplify. And in the leading limit towards the singularity, the equations of motion simplify so much that they can be mapped onto a billiard motion. And the insight of this paper by Thibaut Damour and Marc Henneaux was that the billiard motion actually takes place on a geometry, and the geometry is determined by the Cartan matrix of E10, or by the Dynkin diagram of E10 that we also saw on the previous slide. So this in some sense is a slightly different way of arriving at the conclusion that E10 should be something very fundamental, namely you take just the uncompactified 11-dimensional theory and you look at it very close to singularity, and you already see some of the E10 structures appearing. So this observation about this BKL limit and the billiard motion was then further extended to what I would call the Kac-Moody supergravity correspondence. And in very broad terms, what this says is that there is some dynamical equivalence, and this is a conjecture, between certain motions of on an infinite dimensional symmetric space, E10 over its maximal compact subgroup K of E10, which will play quite some role in this talk. So this is an infinite dimensional symmetric space, which can be given in terms of some Iwasawa parameterization. And if you look at now null geodesics on this infinite dimensional space, which you could think of as massless particle trajectories, these trajectories should be mappable to solutions of 11-dimensional supergravity. So this means that in 11-dimensional supergravity, where the fields are the 11-dimensional space-time metric, GMN of t and x, so t is the time variable and x are the 10 spatial variables, of course, and the other variable of 11-dimensional supergravity is the 3 form, and any configuration of these two fields that solve the equations of motion should correspond to one of these null geodesics over here. So this was the idea which was put forward and with evidence in this seminal paper in 2002. So this is, as you can see here on this side, I've only listed the bosonic fields, and what I want to talk about mainly today is how does this picture get modified or extended once you start adding fermions. So really take the supergravity aspect of the theory here seriously, which means you consider also the gravitino field in 11 dimensions. Now there's a field psi. And what this means is that also on this Kac-Moody side, you not only have the trajectory of a null particle, but you want to have something like a spinning massless particle. So on top of the null geodesic, there's some kind of internal spin space, which is associated with this K of E10. And there's a co-moving spinor degree of freedom, which I call psi of t. And then this equivalence here, or conjectured equivalence, should extend in the right way also to the fermionic fields. And this is what I will talk most of the time about. But I would also like to say that here everything was presented for 11-dimensional supergravity. You can ask the question, why do you restrict to this? And this is a bit in the in this commercial picture, let's say, for M theory. So this goes back to the discovery of dualities between different string theories, where you have type 2A, type 2B strings, but also the other string theories, maybe some 11-dimensional supergravity as a low energy limit, and something that is not really well known, what M theory is. But at least there have the string dualities in certain contexts relate these theories to one another. And it's not exactly known what M theory is, but because we know some of the dualities, this Kac-Moody supergravity correspondence, at least that I was describing on the previous slide, should at least capture some of these aspects. So the question you can ask, and that I'm going to ask in this talk, is there any algebraic structure that at least has some reflections or some traces of this diagram that I was showing on the previous slide? And this is a very unspecific question, so I'd like to make it a bit more specific. And I do this by focusing on certain limits. So the limit, the first thing that I will focus on is I will focus exclusively on the low energy limit, which means I will talk about only supergravity theories. I will not talk about string theory as such. And for this talk, I will also focus more or less exclusively on the fermionic fields. And let me remind you once again what the fermionic fields of these theories are. So the 11-dimensional one we've already seen a moment ago. So there's just a gravitino field which transforms under the 11-dimensional spin group, or I will call it Lorentz group quite often, I think. And for the two 10-dimensional theories, so there are two distinct 10-dimensional supergravity theories, type 2a and type 2b. The fermionic fields look slightly different, namely there are two different 10-dimensional or two 10-dimensional Lorentz groups under which these fields transform. But there, in the type 2b case, there's additionally a SO2 or U1 rotation, where these fields are doublets. So another way of saying this is often that in type 2a, there are two spinors or two gravitini, which I write here as 144 plus 144 bar. So they are of opposite chirality. Spin 1,9 has Majorana-Weil spinors, and these are of opposite chirality. And in the type 2b theory, they have the same chirality and additionally are rotated by this R symmetry SO2 over here. And the Di Latino component here, here also there are 16. These are just the spin 1/2 fields, not spin 3/2 fields. They're of opposite chirality, and here they're of the same chirality, and again rotated by R symmetry. So these are the well-known fermionic fields of these maximally supersymmetric gravity theories in 10 and 11 dimensions. So what else is known about these fields? Here I'm just listing the representations again. So what is known is that you can get the type 2a theory from the 11-dimensional theory by reduction. So that means this type 2a Lorentz group is embedded in the 11-dimensional one. And the branching that is consistent with this is that the 320 components in 11 dimensions, when you look at this branching, they just decompose in the way that they should. By contrast, the Lorentz group of the type 2b theory is not contained in 11 dimensions, which is of course because we don't know, there's no construction of type 2b super string theory or supergravity from 11 dimensions. But there is a common 9-dimensional Lorentz group. So if you do further reduction from 10 to 9 dimensions, the type 2a and the type 2b theories, they come together. So there's a common spin 1/8 subgroup of spin 19a and spin 19b. So this is the same subgroup of that. And also such that the branching of all the representations that I've written above agree. So really these theories, they do come together when you go to 9 dimensions. And this is sort of what I will use as constraints from this M-theory blob that I was showing a moment ago. So the question that I now want to discuss more precisely today is, first of all, is there a group K that contains all these different symmetry groups of the 10-dimensional and 11-dimensional supergravities as subgroups or maybe as quotient groups, as we will see? And does this group K not only have these things here as subgroups, but does it have a spinor representation so that the spinor fields of the group K rearrange themselves in the way that is consistent with the known spinorial content or fermionic content of the other maximal supergravity theories? So this, the way that I'm phrasing this here, this is a purely kinematical question. It's a question about groups and their representations. The other question that I would like to touch upon is dynamical. So is it possible, once we have found the group K and the representation, that one can write down a dynamical equation that is at least related in some sense to the dynamics of the fermionic fields as they are determined in the supergravity theory? So these are two, this is an additional layer to the question. So the first question is easier in some sense because it's just group theory, and I will give you the complete and affirmative answer. The second question, because of the way that this, the Kac-Moody correspondence or Kac-Moody supergravity correspondence is understood in general, I will only be able to give you a partial answer. And so I will mainly focus on the first question. But let me also say that the partial answer arises in the same limit as the BKL limit, or as the cosmological billiard limit. So you treat time separately from space. And for this reason, I will now not give much more evidence, but I will just immediately tell you that this group K that will play the central role in this talk is this group K of E10, which is the maximal compact subgroup of E10. And for the spinors, actually more precisely, you need a double cover of it. But this is a subtlety that will not be, that's more technical than needed in this talk. Good. So here's the outline of what I'm going to say. The first thing is I will define this Kac-Moody group K of E10, or I will mainly focus on its Lie algebra. I will make sure at the kinematic level that these constraints for these embeddings are satisfied and that representations with the right properties exist. So this is sort of this will be the answer to the first question. Then I will move on and give you some details about the second question, namely what about dynamical equations for these fields and what is their relation to supergravity. And after this sort of dynamical interlude, I will go back and discuss more generally aspects of these of this group K of E10, which you can think of as a generalized R symmetry group. So I will discuss more general properties of its representations, how to construct representations, and what we know. And this question is interesting, or potentially interesting, for the following reason, namely that this group K of E10 is of a type that is not tabulated really in any mathematical textbooks. So it's not like you can open a book and just pick the right representation that you're interested in. It's something that you have to invent, or that we had to invent ourselves. And I will tell you how we did it. And this also tells you that there's probably some interesting mathematics to be discovered once you understand more systematically how to construct the representations. And the physical interest in that is, as I will comment, that it might be related to describing more properly also the dynamical degrees of freedom. Then I will make some comments on the relation of what I'm saying to a topic called generalized holonomies, and then most probably my time will be up. So I suppose most people in the audience cannot see the chat of Zoom. I see there are some comments arising. So I don't know, Bernard, whether you want to say them out loud or should I read them out?
As you want, it's the same.
But it's probably better if you just say them. Yeah.
So yeah, so motivated from the finite dimensional case, I first looked for finite codimension subgroups. So finite dimension coset spaces, if you want to have a finite number of degrees of freedom, right? So in 1980, I using the fact that the loop group can be fixed at a finite number of points, say 1, this precisely generates finite codimension cosets subgroups. But it doesn't seem to be useful. And before you go to K10, I just want to mention that the compactness idea of K is absent or difficult to introduce in infinite dimensional case. But in 81, I introduced KE9, a definition of KE9, if you want, using the signature of the killing form, and that fixes everything. So maybe it connects to what you say later. Sorry.
Okay. Yeah. So when you say the signature of the killing form, you so this was in the not in the stationary axisymmetric context, but in the when you do completely spatial reduction, so you had the definite signature, I suppose.
No. I do the space like compactification. So I mean, this is signature of the propagating field, so it's still Lorentz fields. It's in my paper on the conference.
Okay, but if you do space-like reduction, I think the signature on K of E9 is positive definite. On K of E9, not on E9. Yeah.
Or negative, yeah, but precisely that's what I mean. So that's the way to choose what K of E9 should be.
Yeah.
You look for the sign, and then you say this should be a subgroup, and it is, and you find the involution by that.
Okay. Good.
Sorry.
Okay, so then, yeah, let me start with the talk proper. Thank you for the comment. So the first thing is probably a repeat of what Marc has mentioned in the lectures. Namely, first of all, I'm briefly going to review what the definition of the Lie algebra E10 is, because we first have to understand E10 a bit before I can talk about K of E10. So E10 is a Kac-Moody Lie algebra of hyperbolic type, which is completely characterized by the Dünken diagram. And instead of the Duncan diagram, you can also equivalently think about the Cartan matrix, which has a Lorentz signature, which is related to what Bernard was just saying when you restrict even to E9, that there are certain signatures that you have to think about on for the killing form. And the way that this diagram encodes the Lie algebra E10 is through a set of generators and relations. So every node in the diagram corresponds to some SL2 algebra, which I've written here. So I is one of the 10 nodes. And the different SL2 algebras are glued together according to certain relations. And these relations are written down here. So when you take the H elements, which are like the diagonal Cartan elements, they just act with certain eigenvalues on all the other SL2s. And if you take a raising and the lowering operator, they commute unless they come from the same SL2. But the more interesting relations are these ones down here, the so-called Serre relations, which tell you that when you act with one raising operator E of one SL2 on one of the other SL2s, after a certain number of steps, this commutator becomes trivial. And the number of steps depends on whether or not the two nodes in the Duncan diagram are connected. So if they are connected, then this value of the Cartan matrix is -1 by definition. So that means that after 2 steps, you get 0. If they're not connected, you already get 0 after the first steps, which is just saying that the SL2s that are not connected by a line commute. So this is a complete presentation of the Kac-Moody Lie algebra E10, but it's given in terms of generators and relations, which means that if you want to work out what other elements are part of the Lie algebra, you have to look at elements that are generated from the generators. And here, of course, the structure that you have to look at are multi-commutators of these simple generators. And any possible simple generator that you write down has to be subjected to the relations that are on the previous slide. And this is where things get a bit ugly, because it's not always obvious when I write down an arbitrary multi-commutator whether or not this is 0 subject to the Serre or the Jacobi relations. And for this reason, it's not known what the complete list of generators of E10 is. But just from the definition in terms of generators and relations, what you can show is that there's a triangular structure. So there are these Cartan elements that are called H on the previous slide in the middle, and then there are raising and lowering or upper and lower triangular generators. So either multi-commutators of E's or multi-commutators of F's. There are no mixed commutators because using the relations on the previous slide, they can always be reduced. So this is, it's some generalization of a matrix algebra to infinite dimensions. And in order to understand better what are the elements of this, you have to make, or you can make recourse to understanding it from some finite dimensional subalgebra point of view. Because really working with these multi-commutators becomes, after a few steps, very unwieldy. And a good way of arranging these generators is from the point of view of a finite dimensional subalgebra. So this is the thing that is called level decomposition that was used very successfully in this paper by Damour, Henneaux, and Nicolai that I mentioned already. So the way that this works is one takes the Duncan diagram and singles out, for example, one node, let's say the 10th node, and I will show it on the next slide. And then you just grade these multi-commutators by counting how many times E10 or F10 appears. And then this gives you a certain structure on these multi-commutators and makes it possible to classify them, because you know everything has to transform under what is not singled out. So here, this was the node that we singled out. This is the node 10. And the remaining green nodes, they are just nodes for the Lie algebra SL10. So that means that everything that has a fixed number of these elements here will transform in some representation of SL10. It's like branching an algebra to a subalgebra. But the good thing is that, so L is the number of these raising generators associated with the red node. And for a fixed level L, there are only a finite number of generators on each level, which you can geometrically understand from the fact that there's some Lorentzian structure on E10. And this Lorentzian structure means that you have something like a solid hyperboloid, and the intersection with these horizontal planes there are finite. So there are only finitely many elements here in the interior of this hyperboloid. Okay, so with this picture, let me tell you what the representations are for the first few levels in this level decomposition. L equal to 0 means you're not using this node at all. So this is just the adjoint of SL10. And in fact, it's the adjoint of of GL10, because there's a Cartan element that comes from here that combines with the other one to enhance this to GL10. When you use this generator exactly once, you can form a 3 form of SL10. When you use it twice, you get a 6 form. When you use it 3 times, you get a mixed symmetry representation of SL10 with this structure. So there are 8 antisymmetric indices and 1 special one. And these representations are, of course, reminiscent of what I was saying a moment ago about 11-dimensional supergravity, namely that there was a metric which is something related to GL and the 3 form. And these fields you can think of as dual elements. But this list, of course, as you can imagine from the picture, continues infinitely in both directions. So this is just the tip of the iceberg. And once you take this viewpoint from the subalgebra, you can also write out the commutation relations. And here are some examples. So the 3 form with the 3 form commutes into the 6 form. And that's because this level L is preserved by commutators. It's a grading. So L1 with L1 goes into L2, and so on. So this was a brief introduction of or reminder of what E10 is. The main star of the talk will be K of E10. And K of E10 now is constructed from E10 using a certain involution, which I've written here as a transposition. So it's actually an anti-involution, which says that you can take something like the transpose of one of these generators E, which is an upper triangular matrix, and you get the lower triangular matrix, which is F. So the simple generator EI, its transpose is Fi. And this, if you do it twice, you go back. So Fi transpose is EI, and the diagonal matrices HI, they are invariant under this transposition. So this is some kind of generalized transpose. And then this group K of E10, we want to think of as the generalization of the rotation group. So this is the, or algebra, I should say, I'm sorry. The algebra here is the algebra that consists of all antisymmetric elements with respect to this involution. So this is the vast generalization of, if you have just the linear group and you look at the antisymmetric elements in the n by n linear group, you get the generators of SON. So this is exactly here, this K of E10 is like the rotation group sitting inside E10. And something that I already said, but which I'm repeating here, is that it's a very, not obvious, but it's a very important observation that this algebra that you construct in this way, so you just take a good Kac-Moody algebra, you take the antisymmetric elements. This is a subalgebra, but it's not a Kac-Moody algebra anymore. So going to this subalgebra K of E10 is changing the class of objects that you're talking about. And because it's not really one of these very well classified objects, this is where some of the problems start. So when you go to this SL10 decomposition, and you can look at K of E10 in the inherited decomposition, so you write everything in terms of SO10, then there are elements at level 0 in inverted commas because the grading is destroyed. Here, these are just generators of SO10, which are the antisymmetric combinations of GL10 or SL10 elements. Then what used to be level 1, this E generator, is now paired with level -1, its transpose, into also a 3 form. This is now a 3 form of SO10. And now the commutator between 2 3 forms is you get a 6 form as before. But because here you also have the lowering element, the transpose of E is a lower triangular element, you also get a contribution again, which is proportional to the SO10 generators. Okay, so this is something that, I mean, you can work out as much as you like. I mean, it gets complicated pretty soon after that, but you can write down a few more of these commutators to get an idea of what this K of E10 is written in terms of these SO10 tensors. Now, this is about K of E10 itself. So let's talk about some subalgebras of K of E10. The first one is the one that I was just saying in words. So you take the subalgebra of E10, which you obtained by deleting this red node, which is SL10, and then this gives you, by construction, a subalgebra of K of E10 just by restriction. So SL10, the antisymmetric elements in there are SO10. So there is an SO10 sitting inside of K of E10, which is nice. You can also take away these two nodes if you wish. Then you're left with 1, 2, 3, 4, 5, 6, 7, 8. So this gives you an SL9. This is a typo. This should have been a 9 as well. So this gives you an SO9 inside K of E10. And I will call this particular SO9 SO9A. You can also take away another node of the diagram. Let's say this one here. And then you also have 1, 2, 3, 4, 5, 6, 7, 8 green nodes on a line. So this gives you another SL9. And then there's one extra node, which is an SL2, which is disconnected. So you have this direct sum of subalgebras sitting inside E10. And when you restrict to the antisymmetric elements, you get SO9B plus SO2 from this restriction. And these are, if you recall what I was saying before about these M-theory or supergravity symmetry groups, these are exactly the ones that appear when you restrict only to the spatial rotations in maximal supergravity theories in 10 and 11 dimensions. So this is also why I called this one A and B, because they have exactly the properties that you want from M-theory. Namely, SO9A sits inside SO10, which is like M-theory. And SO9B does not sit in there, as you can see, because it goes off in another direction. So the fact that you go this way means that you're not embedding into this subalgebra. Okay, so this means that the subalgebra relations that we want to see from the point of view of M-theory, they are exactly right. Now, the question is, what about representations? Can we construct fermionic fields for this? And for this, it's useful to realize that also K of E10 can be represented in terms of generators and relations in the same way that E10 could be. So one way of saying what K of E10 is saying what E10 is, and then saying it's all the antisymmetric elements. Another equivalent characterization of K of E10 is directly in terms of generator and relations. So if you call the generators Xi, and you can think of them as coming from E10 in this way. So they're the combinations EI minus its transpose. So they're manifestly antisymmetric, but you can also think of these as abstract lattice. And then you have to impose the following conditions. So here there are, again, related to the Dünken diagram. And the difference to the Serre relations that I was explaining before is now that these are no longer homogeneous. So before we just said that the adjoint action, so multiple commutators of one element on another element, gave you 0. But now you see that if you act twice with xi on xj, you don't get 0, but you get back xj. So this is not of homogeneous degree in the axis. And this is complicated. So this relation makes it much harder to satisfy than if it were just, if this term were absent. So this happens when the nodes are connected on the diagram, and if they're not connected, then you still have the relation that they just commute. And of course, on top, you always have to impose Jacobi relations. So if you want to talk about representations of this Lie algebra K of E10, what you have to do is you have to find a vector space, let me call it V, and you have to find transformations of this vector space V, such that there's a map from K of E10 into these transformations that respects all these conditions. So once you do that, you have constructed a representation. And since there are quite a number of these representations here, we can again simplify our lives by looking at something which has manifest symmetry with respect to a subalgebra. So with this, I mean, suppose you take something which is already a representation of SO10, because SO10 is a subgroup of K of E10. Any representation of K of E10 has to be a representation of SO10. So we start from a representation of SO10 and just ask the question, under what conditions can we boost this or lift this up to a representation of E10? And this is then something that only involves this extra node here. So this is something that you can do quite generally. And let me just give you an example of this to make clear that what I'm saying is just a very general construction, and it's not at all related to Kac-Moody symmetries or anything fancy like this. It's just a general method. And the example that I want to give for explaining this is just taking SLN. I was just counting the nodes, sorry, SLN. And if you remove one of the nodes, let's say this outer node, there is an obvious SLN minus 1 sitting inside SLN. And when you restrict to the antisymmetric elements again, here you get SON and here you get SON minus 1. So now what I want to discuss is under what conditions can I take a representation of SON minus 1, which comes just from the green nodes, and lift this to a representation of SON. So the relations in this case here are, you take the Berman generators, xi. So these are all the ones of all the nodes, 1 up to n minus 1. They are just inside SON, there are just 1 minus 1 blocks along the diagonal. Rotations ji, I plus 1. And the consistency relation, these Berman relations I was writing before, that involve the node xi are, sorry, x1 now are that x1 commutes with xj for the nodes 3 up to n minus 1. And there are more interesting relations with node 2, namely these inhomogeneous relations. Okay, so let's see an example. Let's say we take the n minus 1 dimensional representation of SON minus 1 and ask the question, is this something that you can lift to SON? So here on this n minus 1 dimensional representation, these xi generators, now only for the green nodes, 2 up to n minus 1, they look like these small rotations along the diagonal. And now we have to impose these relations for a general ansatz of x1. So if you impose only that x1 commutes with all these little rotations, what you find already is that x1, the most general form of x1, is of this type. So it has to be diagonal, and there are only 2 independent elements. So these all have to be the same in order to commute with all the little rotations here. And then this one can be different, but it also has to be diagonal. And now what we haven't imposed yet are these more complicated relations. And if you do this, you find that x and y have to be 0. Sorry, no, you don't find that they have to be, sorry, you don't find that they're 0, you find there is no solution. So, and the fact that there is no solution, this means that you cannot take this n minus 1 dimensional representation of SON minus 1, and which is the vector of SON minus 1, and turn this into a representation of SON. Of course, this is something that, I mean, is completely obvious and well known to you, but the reason that I'm explaining this is just to show sort of the general strategy of, if you start with a certain representation of the subalgebra, what are the kind of calculations you have to do in order to see that you can lift this up to the big algebra SON, which involves the extra node. And here, of course, we know so much about these rotation groups, it's easy to see what you have to do here to fix this problem. So if you take the n minus 1 dimensional representation and add to it a trivial representation of SON minus 1, then the matrices become one size bigger, and then you can solve all the relations. And of course, what you construct in this way is the fundamental representation of SON. But this is sort of the method that is very useful for understanding or for constructing representations of K of E10. And if you do this now for K of E10, we start from representations of SO10. So SO10 has a vector spinor representation, and for supergravity, we would like to see something like a vector spinor, and the vector spinor of SO10 is 288 dimensional as an irreducible representation. And you can go through the same calculation that I was showing you on the previous slide, and you realize that there's no way you can solve the consistency relations, these Berman relations, just using this 288-dimensional space. But then you can try to ask the same question, is there something that you can add to make a representation of K of E10? And here the natural guess is that you add just a normal spinor, just a 32-component spinor of SO10. So these are 32 real components. And you can write them together in some vector spin-up psi A. So A goes from 1 to 10, and I'm not writing the spinor index. And then it actually turns out that you can solve all these Berman relations, and the solution to these relations were found in these papers. And they look as follows. So under JAB, which is just the set of SO10 generators, you have the usual spinor and vector rotation of the vector spinor. But then you also have this 3-form generator, and this also acts on the vector spinor by certain gamma matrix and SO10 rotations. And the numbers that come out here, this 4, -1, and the precise structure, this is something that is imposed on you when you check these Berman relations. So it's very convenient also in this context to start with something that already has SO10 invariance built in. Then you write down an ansatz for this transformation, and you can fix this ansatz by imposing the Berman relations. And this is really why this method is so powerful. Let me say, so this was node 7, this was node 10. Node 7 is just one of the SO10 elements, let's say J rotation in 7 and 8 plane, and the 10 element is a particular component of the 3-form component, a 3-form generator. And one can just check that this is satisfied. And because all these relations are satisfied, what is proved in this way is that there exists a 320-dimensional representation of K of E10. And this representation is irreducible because you can show that you actually need both pieces, and there's no way of separating them ever again. So this is really an irreducible representation of K of E10. And this is quite remarkable. So this is the first ever found, this is the vector spinor representation that is very interesting from the point of view of supergravity. Now, let's go back, because we're still in the kinematics part. Let's go back to the branching. So what are the properties of this representation when you go to these different sub-algebras that I was mentioning before? There was this sub-algebra that I called SO9A, which consisted of these green nodes. And you can take the formulas that I had on the previous slide and do the branching, and what you find, and this is something that Hermann Nicolai and I did a number of years ago. You can do the branching and you find the representations that I'm writing here. So you find 2 vector spinors of SO9 and 2 Dirac spinors. You can do the same thing under this other SO9 group that you get by going the other way on the T junction, where you also have a manifest SO2, and then you get these representations of SO9 plus SO2. And here, what you find is that there are doublets of SO2, so they have the proper chirality properties as well. And this means that all the kinematical requirements that I was imposing for this representation from the point of view of M theory is satisfied both by the algebra K of E10 and this representation. So this is really, now we have constructed something that is the right type of representation that summarizes or unifies all the different spinors of all the maximal supergravity theories. And this is really something that I still find quite remarkable, because normally one thinks that these spinors, because of the different chiralities and so on, they're very distinct objects. But here, using this language of K of E10, we have constructed something that just combines them in a very natural way. Good. So this was what I wanted to first say about this kinematics part. And next, I will explain to you what is a good equation for these 320 components of this K of E10 representation. But maybe there are some questions before I move on. Mm-hmm. Yes. Yes. So I think exactly. So if it's not simply laced, you know that also in the Kac-Moody algebra itself, the Serre relations can be of higher order. So there's, let's say, if you do it for, I don't know, a type B or type D, you will have the triple, so I see a triple generated at 3 xi's here. And then there will be a relation which is xi, 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 xj, and then plus or minus with a certain number, xi, xj. So, but there are general formulas also for the prefactors and so on. They are just constructed out of the Cartan matrix. But this type of presentation exists for any K of Kac-Moody. It completely, yeah. Yeah, yeah. Sorry, what was the comment? I didn't catch that. So it's not restricted to hyperbolic, yeah. Is that, yeah, E11 and K of E11 looks exactly the same, yeah. Yeah. Okay, so then let me go on with the dynamics part. So the dynamics is, well, we separated out time in the discussion. Everything was just spatial rotations. So the natural thing to look for is just a time evolution equation for this vector spinner. So we have a vector spinner, psi a of k of E10, and the natural guess for its time evolution equation is just that it's covariantly constant, where the covariant derivative is constructed with a k of E10 connection. So there's some connection Q here that you take together with a time derivative. And the connection transforms in the usual connection way under k of E10. And then this equation here at least has all the right local symmetries under k of E10. So this would be a natural guess, generalizing just the massless Dirac equation to this vector spinner of k of E10. So this connection, you can also, I mean, it's a very abstract thing to start with. It's just a connection valued in the Lie algebra k of E10. But you can expand it out again in the level decomposition. And then what you get is you get just the part which is like a rotation part, SO10, and then you get things with a 3 form, with a 6 form, and so on ad infinitum. So this is just expanding out the most general element in this vector space. And then with this just general expansion of the covariant derivative using this expansion of the connection, what you can do then is you can use the explicit formulas for the representation, because we know, sorry, let me go back one slide. So here you have to look at the action of this k of E10 element on psi. And this is exactly what I constructed on the previous slides. So here I write out what you get. So here you get this is just the spinor rotation, this is the vector rotation, and then you get many terms from the higher level fields, which you see come very specifically because it's a very definite representation that we're looking at. And of course, this goes on forever. So this is just something that is the expansion of this covariant derivative of the spinor field. Now the question is, what does this equation here have to do with anything in supergravity? And in order to do this, what you have to do is you look at the equation of motion in supergravity, in 11-dimensional supergravity for the gravitino field. And because of this split of time and space that I was doing, there are certain field redefinitions and decompositions you have to do, and gauge fixings also for some of the fields. But you can also, I mean, this is not doing anything to the supergravity equation, it's just writing it in a very specific form. So you do a number of gauge fixes and field redefinitions, and then the equation that you find looks like this. So this is the exact full 11-dimensional gravitino equation written in this sort of gauge fixed form. So you see, you also have many more terms than you would have expected because I've broken covariance and I've done some other funny things. But all these funny things I've been doing, they're exactly the things that you would do also from the point of view of cosmological billiard. So it's nothing, nothing completely outrageous. So this is now the equation in supergravity, the exact supergravity equation, to lowest order in fermions, I should say. And you want to compare this equation to the one that I had on the previous slide for the covariant constancy under K of E10. So here, if you ignore this last line, because this last line has explicit space derivatives of the spinor fields, and also some other, these are also explicit space derivatives. So if you ignore this last line, and in the K of E10 equation, you ignore all the things that are called dot, 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 then the two equations are exactly identical. You can map all terms to one another using this so-called dictionary. So this is just connecting the components of this Q of E10 connection, K of E10 connection to fields in supergravity. So the SO10 connection is nothing but this certain part of the spin connection. So this is not very surprising. The reform connection part is nothing but a certain part of the four-form field strength. So this is like the electric part of the field strength. The six-form connection part is like the magnetic field strength. And this mixed symmetry connection part is like the dual of the holonomy. So this is just what you get from comparing these fermionic equations of motions. And I should say, let's see if I wrote it here. This is exactly what you would also find and what was found in this seminal paper by Damour, Henneaux, and Nicolai, just from the bosonic analysis. So this shows that there's a certain striking agreement between the bosonic and the fermionic way of looking at this supergravity Kac-Moody correspondence, because it's exactly the same dictionary that you find either from the bosonic or from the fermionic equations. And here I've shown this only for the 11-dimensional supergravity, but you can also do similar analyses for type 2a and type 2b. Good. So this was what I wanted to say about the dynamical part. Now let me make a few more general comments. So something that I said in words, but I didn't emphasize what it means, is the fact that we had a 320-dimensional representation of K of E10. So what does this mean? That it means that we have a finite dimensional vector space, 320-dimensional, and an infinite dimensional algebra acting on this. So that means that there's a large kernel for this representation map. So there are infinitely many combinations of the K of E10 generators that do not act at all on this vector space. They're just mapped to 0. But this is in this representation. So this is not saying that the generators are 0 as such, but this is a representation-dependent statement. And in mathematical terms, this is what is known as an unfaithful representation. And it's unfaithful because it does not represent all the elements here faithfully. Many of them are mapped to 0. And the ones that are mapped to 0, they form an ideal. So this to each such representation V that is unfaithful, you can associate an ideal, namely by just taking all the elements that act trivially in the representation. And unfaithfulness in mathematical terms just means that this set is not just the 0 element. Now, what is interesting is you find really an ideal. I mean, it's a two-line calculation to check that the elements that satisfy this, they are closed under the K of E10 Lie bracket. And this is completely general. So what I'm saying here is not specific to K of E10 in any way. And so any unfaithful representation gives you an ideal, which means that you can form the quotient algebra. So you take the original algebra, K of E10 in this case, and you quotient by the ideal associated with this unfaithful representation, and you obtain a quotient Lie algebra. And this quotient Lie algebra is some subalgebra of the transformations of the vector space V of the representation. And you can ask the question, what quotient Lie algebra is this? For example, for this 320-dimensional vector spinner that I was mentioning, spin 3/2, this quotient Lie algebra was worked out actually quite some years after the construction of the representation, and it turns out to be the orthogonal group of split signature SO288, 32. And this might be a bit surprising because of one thing that I didn't emphasize actually before, which is related also to the comment by Bernard Julia, namely that you can ask the question on K of E10, is there an invariant bilinear form? And the answer is yes, it's inherited from E10. And you can ask for the signature of this invariant bilinear form. And in this case here, it's a bilinear form of definite signature. So this is what you normally think of as a compact Lie algebra, something where the Cartan killing form is definite. But what we find from this construction, this is really something special to the infinite dimensional case, it will never happen in a finite dimensional case, is that when you construct this quotient Lie algebra, you can find quotients that are not compact. So even though you think of this big algebra K of E10 as being compact, the quotient is non-compact. So this is something that is quite remarkable, I find. But this is just something that comes out of the analysis if you go through it. And this is what you get for the 320-dimensional representation. Now, the question is, are there other representations? And the natural candidate, and in fact, historically, this was done before the vector spinner, is to look at the Dirac spinner. And the reason that this is natural is because this is the matter field in 11-dimensional supergravity, but supergravity has a supersymmetry parameter with 32 components. And so you would also expect there to be a 32-component representation of K of E10. And this is actually easy to show that this exists as well and how the gamma matrices act on it. And also this one here has the correct branching or decompositions under these subalgebras into chiral or achiral, type 2b, type 2b, and things, type 2a, type 2b, and things like that. And well, these are now two representations, and I now want to spend the next few slides on discussing how to construct even more representations. Yes, please. Very good. So I didn't write it, but what you get in this case is just the rotation group SO32. So in that case, it's compact. And the 32 components are just the spinor, sorry, the fundamental representation of SO32. So you could ask the same question if you wanted for E11, actually. So in E11, what you get for there's also 32 representation of K of E11, and the quotient in that case is SL32. So then it becomes non-compact. But that's not so surprising because you have now involved time in the game. Okay, yeah, so in order to explain how to construct more representations, let me give you a different way of writing the Lie algebra K of E10. And the way to do this is by using the root space decomposition of E10. So the Lie algebra E10 has a certain set of positive and negative roots. Let's focus on the positive roots. And they can have higher multiplicity. So that means that there are many generators associated with a given root. And now for each of these roots, we can write down a generator also of K of E10 when alpha is a positive root. And there are as many, again, as the multiplicity of alpha. So this is just an abstract way of writing all possible generators. But of course, this doesn't tell you anything about the structure constants. And in fact, even these numbers, the multiplicities are not known. But it's just some abstract way of writing the algebra elements. The good thing is for what is known as real roots, so these are the ones that are on the outside of this hyperboloid that I was drawing on the picture, the multiplicity is 1, and you can forget about this label I. So then you just, I'll just write J alpha for short. And the action of K of E10, let's say on this Dirac spinner, then can just be written in terms of some Clifford element in the SO10 Clifford algebra, which is determined by alpha. So for all real roots alpha, I can construct some Clifford element gamma of alpha, and then this becomes the action of K of E10 on this spinner component. And the way to construct this Clifford element can be done using what is known as the Wall basis. So this is really what comes from the billiard analysis, from the cosmological billiard. Yeah, so in this Wall basis, there are basis vectors EA, and they satisfy inner product given by the de Witt metric, which I believe will have shown up in the lectures. So this is just a certain indefinite 10 by 10 preferred metric. And this is an adapted basis for that metric. So if you expand the root, which normally is expanded on the 10 simple roots, now in this Wall basis, and take the coefficients in this Wall basis, alpha sub A, and here I'm changing the font for A because this doesn't have any meaning in terms of SO10 vectors or anything like this. It's just a label. So if you take these 10 components alpha A, then you can take the 10 gamma matrices of SO10, gamma 1 up to gamma 10, and raise them to these labels. So this is a way of associating for each alpha an element in the Clifford algebra. And this construction of a map from the root lattice to the Clifford algebra is something that we didn't invent. So this is something that already shows up in certain conformal field theory constructions of spinners, which goes back to, or which you can find, for example, in the review article of Goddard and Olive. So this is just a map from the root lattice into the Clifford algebra with certain properties. And now written in this way, the K of E10 representation now has to be checked again. If one wants to recheck the K of E10 representation, one has to recheck the Berman relations or Berman conditions. They are now turned into certain commutation and anti-commutation relations for these gamma of alpha, depending on whether alphas are connected or not. So, for example, if alpha and beta have inner product -1, so this would be the case for connected nodes on the Dynkin diagram, then you find that from the prescription I was giving on the previous slide, that the commutator of the associated Clifford elements is just plus or minus, so there's a certain cocycle here that I don't want to get into, the Clifford element of either the sum or the difference of the two. So actually it doesn't matter because whether you take the sum or the difference of the two, because from this definition here, let me go back, you see that because each gamma I, so each gamma 1, gamma 2, gamma 3, if you take gamma 1 squared, it's the identity. They all square to 1. So if you change a label from plus to minus, you go an even number of steps by construction. So it doesn't matter whether you add or subtract labels in terms of this Clifford element. So this map for Clifford elements that I'm describing has the property that the commutator is very simple and the anti-commutator is even simpler. Namely, it vanishes if alpha and beta have inner product -1. And then there are similar things that I'm not writing that you can do for other inner products. And these rules for these Clifford elements, they are sufficient to check the Berman relations. So you can translate then the Berman relations by taking for these Clifford element alpha I, the simple roots, and using this simple property, you can just check again the Berman relations. Good. So this was how you can rewrite the spin 1/2 field, the Dirac spinner. Let's go back to the representation that we started with, namely the vector spinner. And in order to write the vector spinner in this language, it's actually useful to make a certain redefinition, because I emphasized before these A labels that I had in the Wall basis, they are not SO10 labels in any way. They're different labels. I mean, they're more properly thought of as SO1,9 labels actually, but we want to break SO10 in order to connect to them. So one way of breaking SO10 is by just taking the component psi A and multiplying by a gamma matrix, gamma A, without summing on A. So this clearly breaks SO10 covariance, and it's just a field redefinition on this 320-dimensional set of fields to what I call phi typewriter font A. So now what you want to do in order to describe the action of K of E10 in these variables, you have to write down what is J of alpha on one of these variables. And this now has two parts. So one part rotates this typewriter label, AB, and then there's also another part that rotates the spinner part that I'm suppressing all the time. So you sort of have disentangled the spinner and the vector part in this transformation rule. And here you take the same gamma alpha as for the spin 1/2 fields. So now, in order to establish that this is a representation, you have to make sure that the Berman relations are satisfied, and the Berman relations now, they translate into conditions using what we know about gamma of alpha. They translate into conditions for x of alpha. And this x of alpha is just a 10 by 10 matrix, so it's a much simpler problem than solving conditions for 320 by 320 matrices. And also here, somehow this looks very nice because you're just writing something for alpha, so you have a limited set of building blocks for every alpha. And making an ansatz, you can easily solve these Berman conditions by taking for x of alpha something that is expressed in terms of the components of alpha and just the Kronecker delta. So this will solve all these Berman relations. And now you will have noticed that I'm no longer distinguishing certain nodes on the Dinkin diagram. I'm just treating them all democratically. So this is a different way of constructing this representation now, which heavily relies on this Clifford map, actually. But because it's now treating these alphas very democratically, you can try to do something similar. Let's say you take, instead of phi A, you take now phi A1 up to AN. And let's say you take them symmetrically, because this is something that is very suggestive, let's say, from higher spin fields. And you can ask the question, if I now look at these symmetric higher spin fermions, so I'm always suppressing the spinner index, can I solve the Berman relations with just making an ansatz for this x? And this is the question that we asked, Hermann and I. And the answer that we found is actually when you take n equal to 2 or to 3, you can find solutions. But then we were very motivated and went on, and we didn't find any more solutions for higher n. So I think we checked up to 10 or maybe even 11, making this ansatz for phi, making the most general ansatz for this x, and imposing the Berman relations and just checking whether a solution exists or not. And there were only 2 solutions that we found in this way. And here I'm writing down the solution for n equal to 2. You see it's still very simple. The one for n equal to 3 is a bit more complicated and actually involves an algebraic number square root of 7, I think. No, square root of 10 probably. But it's still possible to construct that representation for n equal to 3. But we have so far, despite many efforts, we have not been able to find any more solutions for K of E10 representations. And I should also comment that some mathematicians, Ralf Köhl and Robin Lautenbacher, have picked up on this and have reinterpreted, let's say, this formula here from some Weil group action. So there's an understanding of at least some of the representations that we find using different constructions. But at least we have found some additional representations. So let me say that there's something, I mean, why are we interested in these representations? So one reason why we're interested is just out of curiosity. But another reason is also that I was emphasizing before that the representation, the spin 3/2 representation, is unfaithful. So somehow we know we're not capturing the full beauty of K of E10. And it would be much nicer to have some faithful picture of K of E10. And one way of getting there is by constructing a sequence of more and more complicated unfaithful representation whose infinite size limit would then give a faithful image of K of E10. And from the point of view of the Kac-Moody supergravity correspondence, one possible way of thinking about this is that these higher spin fields, and that's another reason why we took symmetric indices, maybe they will be related to higher and higher spatial derivatives of the gravitino field. So this is sort of getting a better and better derivative approximation of the true dynamics of supergravity, not just the time derivative, but getting all the derivatives. So this is one of the main motivations why we're studying these things. Yes, yes, please. That's correct, yeah. And I mean, I can give you one faithful representation, which is the adjoint, but of course we're interested in spinorial representations. And there are no good spinorial infinite dimensional representations that are known. But yeah, faithful would be infinite dimensional because the algebra is infinite dimensional. Thank you. Excellent question. So this is something that we would like to do, and I will comment on that also in the conclusions, but let me say one thing, which is that here, I mean, we're using this sort of funny basis for the fermionic field. So this is not really, these indices are not, and that's why higher spin is in inverted commas, these indices are not really Lorentz indices. So you can ask the question, and I will actually show you on the next slide, what are the Lorentz representations associated with this, and you will see that here they look symmetric, but they will turn into something typically anti-symmetric, which is not what you would expect for gradients. So we don't know, we have these solutions, but we have we haven't found for these particular ones a dynamical place in terms of gradient expansions. We haven't found that yet. But you could ask the question independently of that, can you construct any interesting dynamical model with these things? And this is also something that we wish to investigate at some point. But these, at the moment, these are just representations. They haven't been connected to any physical model. Does that answer the question, I guess? Ah, okay, I didn't hear any, sorry. Yeah. Okay, yeah, so as I promised, let me show you what is the branching of these things. So for n equal to 0 and n equal to 1, so this is the spin 1 half, this is spin 3 halves. Under SO10, they are just what we already knew. So this is just the 32 component spinner, and this is the vector spinner that decomposes in this way. For n equal to 2, you have that many components by just counting, and if you do the branching, you get these representations of SO10. So this is spin 1 half field of SO10. This is the spin 3 half fields of SO10. And this thing here is actually, I should have drawn the Duncan diagram. This is a antisymmetric tensor spinner. So this is something that has 2 antisymmetric indices under SO10 and 1 spinner index. So it's not, it doesn't look like a gradient, it's a symmetrized gradient of a usual spinor field, actually. If you do the same thing for n equal to 3, you get more complicated diagrams. And actually, I should remember, I think this one here, this is a hook diagram. So it has 3 boxes of SO10. It's the hook and then a spinor index. And this is the same one that we had seen before. So these representations, they look, this is the 3 form, I think. They look very different from the point of view of SO10 compared to these typewriter font indices that I was using for constructing them. And for none of these, we have a dynamical model, but how to realize them in terms of some free fermions. We also looked at other subalgebra branchings, which I'm not showing you. And this is what I was saying in answer to the question a moment ago, almost that for the cases n equals to 2 and n equals to 3, actually, we don't know how to make the change of basis. We know what the representations are, but we don't let me show you the formula that I'm referring to. So here there's a formula that connects the SO10 covariant spinor to this non-SO10 covariant spinor. And we don't know what is the generalization of this formula for the other representations that we found, which is part of the reason why we don't know how to write a good physical or dynamical model for this, which we would like to write with SO10 invariance. But nevertheless, I mean, these are perfectly fine representations of K of E10. And what you can also check is that they are truly spinorial representations in the sense that they are double valued when you rotate one. So they're representations not of the group K of E10, but of its double cover. And one way you can see this is because you can check the Weil reflections, which should be normally elements of the rotation group, and they are of higher order than they are for bosonic fields. Very good. So yeah, actually, so let me just make a few comments before ending on generalized holonomy, unless there's a question. Was there a question? No. So what is generalized holonomy? So this is something that was very much looked at or suggestive some years ago, actually, when you look at the killing spinor equations of supergravity theories. So let's start with the usual Lorentz covariant derivative of a spinor field. So this is just the usual spin connection, let's say SO1, 10. Putting this equal to 0 would be a Lorentz covariant constant spinor. But this is not the correct killing spinor equation in 11 dimensions, because in 11 dimensions you also have a coupling to the matter fields. So there's an extension of the usual spin covariant derivative involving the matter couplings, which involve different gamma matrices. And the idea of generalized holonomy is that normally you look for holonomies in this Lorentz group, but here you have also other gamma matrices floating around. And maybe you should think of holonomy as being something that is valued in the algebra generated by all these gamma matrices. So this is, if you take all these gamma matrices and look at the algebra that they generate, you end up with this SL32 that I was mentioning, actually GL32 that I was mentioning before. And this is something that people think is quite interesting, because maybe you can use this to classify certain G structures, or I mean, this is certainly a group that has to play some role. But this idea, oh, actually it's SL, I think it, well, maybe it's even GL32. So the problem with this thing is that, as I will explain a bit more on the next slide, this group here looks suggestive from the point of view of the Clifford algebra, but actually this is only at the algebraic level. And there was work by Ari and Corinthius who showed that there's no proper lifting of this group to the of the algebra to the group level. So even though the algebra looks to be SL32, there are certain problems with the double valuedness when you go to the group level just for this. And another problem that you have with this is that, so this is what I was already saying. Another problem is that these groups, SO32 that Marc asked about a moment ago, and SL32, they are suggestive when you look at the Dirac spinor, so at the killing spinor equation. But in order for this to be something acting in the full supergravity theory, you also want to act on the gravitino field. And clearly, there's no way of taking any of these groups and acting on the gravitino components. And I suppose you can already see what I'm going to say next, namely that the groups that I've constructed, and this is one of the main things that I've been going on about at the kinematic level, is the Lie algebra K of E10 can act on all spinors, so not only on the spin 1/2, but also on the spin 3/2 field. And something that is also interesting is that these sort of global problems that were pointed out, they disappear. So these representations, they also lift correctly to the double cover, both for the Dirac spinor and for the gravitino field. The effective symmetry that you see on a given representation, as I was emphasizing for unfaithful representations, is not the full symmetry, but you only see a quotient symmetry. And the quotient of this K of E10 to the Dirac spinor is SO32, but as I was saying, when you take the quotient for the Gravitino, it's actually SO32, 288. So you get different quotients depending on the representation. So you have to allow for different groups. So there's not this finite dimensional generalized holonomy group that plays a role, but it's actually an infinite dimensional holonomy group. This is what I want to propose. There's an infinite dimensional holonomy group, and it only looks finite dimensional because you look at different finite dimensional representations. So this is really one of the most striking features of this construction, really, that there is this thing that looks really nice from this point of view. Very good. So let me summarize. Just repeating what I was saying during the talk. So the group K of E10, or the Lie algebra that I was mainly discussing, is a very beautiful way to describe all the different fermionic fields of maximal supergravity theories, type 2a, type 2b, 11 dimensions, and also when you reduce. So all the maximal supergravity theories, they all come just from one object looked at from different angles. This is the kinematic part. I was also explaining that dynamically, you can write down a very simple equation, which is just covariant constancy under K of E10. And this covariant constancy, again, if you decompose it and massage it, it looks very similar to the supergravity Gravitino equation. There are discrepancies. I mentioned that there are some parts on both sides that you have to get rid of, and maybe one way of solving that problem, or this annoying thing that you have to ignore certain terms, is related to the fact that we were dealing with unfaithful instead of faithful representations. I just mentioned it's a good candidate for our generalized holonomy group, and it's also very interesting mathematically. So there are mathematicians getting involved. Now, what are the things that would be nice to do with these things? One is, of course, the construction of faithful spinors, and then connected to these gradient expansions or gradient conjectures. Another thing that, because I was only talking about the fermionic sector, something that you could try to do is to connect the bosons and the fermions more closely. And you want to do it in such a way that you have also local supersymmetry compatible with K of E10. And this is something that hasn't been done. So there are also certain, let's say, obstructions to doing that, taking a bosonic null geodesic, as I was mentioning in the beginning, and putting a spinor on that, such that you have local supersymmetry. And we believe that these obstructions are also related to the fact that we are talking about unfaithful spinors. So I was ignoring many of these dots in the K of E10 part. So this is the higher level generators for the dictionary. And of course, here the main question, and this has been around for quite some time, is how to properly interpret these the action of these higher level generators. Are they just implementations of gradients? Are they implementations of certain electromagnetic dualities? What does this mean for spinors? So this is something that I believe is not understood at this moment. And well, this was something I already said in answer to the question before. So these higher spin representations that we found, we don't really know what is the dynamical meaning of them. So there are certainly representations, but are they related to any of these problems? I have some doubts, but can you still make sense of them in just a separate higher spin or dynamical system? Is there any role for them to play as a dynamical object? So maybe with this list of questions, I turn to questions. Thank you.
Thank you very much for this very clear talk. So we have, well, we already asked a few questions, but we have time for more. So yes.
How do you expect K of E11 to fit in this full scheme? Because you said already in the beginning of your summary that K E10 captures everything actually from supergravity.
Yeah. So did you hear the question, or should I read?
No, I
okay.
didn't.
So how do you expect K of E11 to fit into this picture, given that already K of E10 contains all the interesting information. So why K of E11 in a sense?
So K of E11, so where should I start? So K of E10 in some sense only deals with the spatial rotation part. And when I was talking about the, let me go to the slide with the dynamics here. In the fine print down here, I was saying I'm fixing a certain gauge for the zero components. In some sense, I'm removing the zero component, which is a supersymmetry gauge. So I can only do this in a gauge fixed form. So certainly one way of how K of E11 would come in is that if you remove all these gauge fixings that I was talking about. So also there's a Coulomb gauge fixing, which removes certain component of the three-form field. And actually, I'm also using a zero shift gauge. So yeah, it's written here. So K of E11 or E11 would be relevant when you remove all these gauge fixings. And it's easy to check that from the point of view of the kinematics. There is all the things that I was highlighting for K of E10 are also true for K of 11. You just get covariant spinors and they transform in the right way. But the problem will be there is no natural candidate for this, at least I don't know of any, for this dynamical equation. So the kinematic, so I know Guillaume will scream at me in a second, but so at the kinematic level, I mean, K of E11 is very nice, but in order to write down this this equation here with all the right gauge invariances, I mean, so one thing is to write down something that has the right transformation properties of K of E11, but you also want to have it such that it has the right gauge invariances, and I think there is no direct candidate for that.
Okay, thank you.
But I don't know whether Marius was.
I think that's probably the unexpected answer, or an answer, a satisfactory answer. Any other question? So maybe I have two more quick questions. One is, all these finite dimensional representations of K of E10 that you exhibited are in some sense spinorial. They would be double valued, etc. Do you have also finite dimensional bosonic representations? I mean, just, I mean, maybe they are not physically relevant, but just to know.
Well, there's one that actually is physically interesting, at least, which is that if you take the spin 1/2, the 32 component representation, you can form its symmetric tensor product. Okay. So this is like taking the anticommutator of two SUSY transformations, and then you get a 528-dimensional bosonic representation, which is like the algebra of central charges in supersymmetry. So this is something that you would that could be physically interesting in the sense that this is what might be connected to like space translations and things like that. So it's from the point of view of the space-time de-emergence, I think this representation is not completely uninteresting. It could be embedded in, let's say, an infinite dimensional translation thing. This could be some interesting finite dimensional quotient, which is something that Guillaume Bossard, Ergin, Seskin, and I actually have speculated about in the context of E11. So this exists, but I should say, of course, one more comment on this. If you take a tensor product of two 32 component representations, you get a bigger representation and it's bosonic, but it's not more faithful. So the quotient algebra doesn't change in that construction. So you're still left with SO32. It's like taking an SO32 tensor product.
Okay. Yeah, thank you. And then perhaps another question. On one of your transparencies, you mentioned, I think it was the n equal 2 case, that if you look at the Lorentz transformation properties, you have a spinorial 2 form or something like that. Is it of interest to dualize on the form indices and see, I mean, sometimes by duality you connect different derivatives, or I don't know if that is of any interest.
I think it would be interesting.
A dual description of the spin 3/2 field, normally it's psi lambda, but sometimes in some dimensions psi lambda mu is good, and or psi lambda mu nu, would also, I mean, a three form with a spinorial three form, spinorial two form, at least at the free level, is something that you can play with. I don't know if that is of any interest here.
I think it would be of interest, and we've been trying to do this for some time, but it hasn't.
Yeah, in
seen
terms
the
it would
light.
be different. I mean, you would not. Yeah, the two form would not have enough. I don't know. Yeah,
Yeah.
that would depend on the dimension, clearly.
Yeah.
Yes.
And also one thing in response to that question that I always have some slight hesitations about is that dualization for fermionic fields doesn't work in the same way as for bosonic
That's
fields.
right.
Because of course the equations are first order instead of second order.
Mm-hmm. That's right. Yeah. Yeah, just to try to understand these representations.
Yeah.
Okay. Any other question? Well, if not, let's thank Axel again. Thank you very much. And
Thank you.
well, we hope to see you physically in Paris at some point.
I'd very much love it. Thank you. Yeah.
Okay. Thank you very much. Bye-bye.
Thank you. Bye.